There we go. Thank you so much for the introduction. I've had a wonderful time. It's my first time in Taipei. So hopefully you will not be regretting that I came. So let me start. So as you could see from my abstract, I have a lot of references that I should mention to do this justice. So rather than asking for permission, I'm going to ask for forgiveness. And I will run through. This doesn't seem to be working with me. Is it okay? Am I too loud? Is it better? How about now? I'm pretty loud without it, so.
But they need recording.
Oh, I see. Oh, I wish you hadn't said that. All right. Okay. So yeah, rather than ask for permission, I'm going to ask for forgiveness. And I put in, as you probably saw, quite a few references in my abstract. So rather than me going through and still not doing all of the people that have done work on this justice and waste an extra couple of 20 minutes, I'm going to just go through the main points behind the motivation of the Penrose conjecture. And I'll give references as I go along. But I'm hoping the introduction that I'm about to give is more something to motivate rather than for you to take too deep to heart. So let's get going. So what is the Penrose conjecture? So I'll start just by motivating what the conjecture is. Well, we start off with an isolated system. A number of our speakers this week have already given credence to what that means. And just for the moment, we can imagine space then within a space-time of an isolated system at an instant of time as being geometrically represented by an asymptotically flat Riemannian slice. Okay, so the idea is you have some black hole or a cluster of stars at the middle of your space-time, and the further away you move, the more you start to look like Minkowski space. And what you can think of as these Riemannian slices representing is the infinitesimal, the rest space for a particle that you're approximating as you go far out, if you like. You can think of these slices as the rest space for a particle that you're starting to measure as you approach infinity. And then as the geometry starts to collect and you start to see at infinity this particle, we can use these asymptotically flat Riemannian slices to measure the total mass of the system. Okay, so I'll say more about that later, hence why I'm still being vague. One comment on that, if you have your asymptotically flat slice, the way that we measure total mass is by looking at large coordinate spheres as we go out to infinity. And we actually use something called the Hawking energy to measure the energy of that slice and therefore the mass. Okay, so that's what we think of as total mass. Now, we've also heard, I think before in previous talks, that we have these theorems by Hawking and Penrose, the singularity theorems, and what they state is that for reasonable data, i.e. an initial condition that measures a reasonable physical system, geometrically that's represented by the slice and its intrinsic and extrinsic geometry, they find in their theorems that this will give rise to singularities whether we like it or not. So we have to deal with it. Okay? Now, one of the main reasons for why this conjecture pops up from Penrose is that given these singularities, a hypothesis that Penrose formulated to deal with the fact that these singularities show up is something called weak cosmic censorship, which I know we'll hear more about next week. And very roughly what this weak cosmic censorship says is even though we see these singularities popping up in our space-time and all the problems that can come with that mathematically, weak cosmic censorship saves us by saying that this singularity, although it exists, will be enveloped by an event horizon. And therefore, we are shielded from its chaotic behavior. All right? So that is by far the most troublesome assumption that we make on our way to the conjecture. So we can represent this event horizon by something called a Kata Penrose diagram, which Jordan mentioned yesterday. And we can compactify, because it's an isolated system, our space-time into this diamond shape. And then the event horizon is the past, the future, null infinity, which Muta said some words about on Tuesday. And the event horizon we see as a null hypersurface. Okay, so if we only assume one black hole then from Hawking's black hole topology theorem, we expect any cross-section of our event horizon to be an S2, a sphere. And if I draw this asymptotically flat slice in this diagram, you can see it represented here, and we idealize space-like infinity, these large red spheres, as a point, and each point on this diagram is a collapsed S2. So every point on this picture you should think of as an S2. So as we go to space-like infinity along this slice that you see down here, you're approaching space-like infinity, and this is where we measure the total mass of the space. And therefore, the cross-section of this slice with the event horizon is what we will think of later on as a black hole. Okay? So there's the picture, and there's my asymptotically flat slice inside of my space-time. Now we have an area theorem due to Hawking with work contributing from Shane and Galloway that says that when you look at cross-sections of this event horizon to the future, so we think of time as pointing up and space, the uncompactified space, as being horizontal, as you slide your point up the event horizon, you see that the area will increase. All right? So that I just represented here by d by dt of the area of these cross-sections being non-negative. All right, now we've already heard quite a lot about the Bondi mass loss. So what we see along these S2s on future null infinity is that as we slide these to the future, Bondi mass loss tells us that the Bondi mass will decrease as we go to the future. So we start from our slice, and along the event horizon and along null infinity, we go to the future towards time-like infinity. The mass decreases and the areas of the cross-sections increase. And for very large times, we expect an isolated system after all the gravitational radiation has radiated away, that the stability of space-time will approach a solution of the vacuum Einstein equations, namely a rotating black hole or the Kerr space-time. And work regarding this stability has a very large number of contributors, including 3 members in the audience. So my apologies for not saying too much more, but we expect as we go to the future that the space-time to settle to a Kerr solution. But why is that relevant for us? Well, a Kerr solution has an event horizon. So if you think of the event horizon inside this yellow diamond, it's actually a killing horizon, or it's approaching a killing horizon. And what's significant about that is that all cross-sections up here are isometric then, which means that no matter how I take my cross-section in Kerr, the area will be the exact same. And by a direct calculation on the geometry of Kerr, we see that the area is bounded above by precisely the Bondi mass at scribe plus, using that formula with the square root. Okay? So there's our space-time. To the future, we see areas increase, Bondi mass decreases, and when we hit inside this diamond, we have this inequality. And that's exactly what led Penrose to his conjecture in 1973. So where's my, oh, there we go. So that finally leads us to the Penrose conjecture, which says, if I go back to my original slice, which I'm busy erasing right now, and I measure the area of the black hole, because of the increase in area, decrease in Bondi mass, Penrose concludes that the area of my black hole in the slice is therefore smaller than the area as I approach my Kerr space. This we show explicitly is smaller than the Bondi mass, and this has decreased from the total mass of the slice. So there's the Penrose conjecture. Okay. So why do we care? That's a great little argument, but why do we care? Let's see. I guess I'll put, let's put this over here. And the reason I gave cosmic censorship that red star is it's by far the one that I'm erasing right now. It's because it's by far the most questionable assumption we've made, and it was actually Penrose's original motivation to come up with this inequality was because he didn't believe it either. And after many attempts to show that it was not true using the explicit solutions at the time, change direction into maybe showing that this inequality that I just wrote down on the left board is in fact true. So why do we care? Mainly cosmic censorship. All right, so this is of course a fundamental assumption that we've made here on the structure of solutions. Einstein's equations. And if the Penrose conjecture is false, it will likely imply that cosmic censorship is also. All right, so that's the first thing. The other thing is, well, it's a really beautiful geometric inequality. And it bounds a global invariant of our space-time by the area of a black hole contained within. So even for its differential geometry, it's very, very interesting to study, if true. So let's see, I'm not being very smart about this. So I'm worried, I guess I should be putting this up and then writing down here, but then I think most of you guys won't be able to see. There we go. No, whatever. If I'm in the way, just tell me to move.
So this part on black hole stability, that's a part that's more susceptible to Penrose?
More susceptible to Penrose?
More susceptible than Penrose we said.
Yes, yeah. I mean, you could argue that if Penrose conjecture is false, maybe one of the other assumptions are false, but by far this is assumed to be the most likely to be destroyed. So there's a lot of, many of those things that I said by have not been fully satisfied, yeah. So I am very much leaning here on intuition, originally from Penrose than fact.
That little chain of inequalities, so that it's a true little argument for perturbations of care, and this relationship between area and mass, is it thought to be true for general isolated systems or just perturbations of care? Or?
Generalized isolated system, if you assume the picture that I drew is true, so you settle to K. So, I mean, yeah, exactly. You're assuming whatever the isolated system is, it will approach perturbations of K. It's one of the stability assumptions, yeah. So, yeah, like I said, I'm committing a couple of heresies here, please.
But what you meant is Hawking's area theory. That's assuming event horizon.
Yes. So, yeah, I'm actually not talking event. It's all of these are true for cross sections of the event horizon, but I'm going to be talking about something later called the apparent horizon. But I'll justify why this will imply what I'll call eventually the null Penrose conjecture. Yeah. So yeah, I'm being very vague, but I will clarify everything as I dig more into the mathematics. So that was number one for why do we care. Number two, just because I want to put it on the board. It's just a nice geometric bound. Global invariant of mg. Namely, the mass. All right, so that's the Penrose conjecture in a very small nutshell. I'm going to be attempting to answer, at least in part, a more ambitious question. Okay, so a more ambitious question. How do you spell this? Ambitious question. All right, so look that we argued for a asymptotically flat slice. Let me draw my Penrose diagram again. And this is scribe plus, this is scribe minus, this is our event horizon. Rather than taking an asymptotically flat slice, I'm going to take a diagonal slice. call that omega. All right, so if we believe that time is to the future and space is horizontal, then what this slice represents is a relationship equally weighted between time and space, and that gives rise to what we call a null hypersurface. So omega, if we assume that the event horizon is an S2 cross R, looks something like this. All right, and the cross-section I've drawn up here is given over there as such. And if we idealize our past null infinity, we've got a cut here at scri minus, and we have our event horizon. And this is omega. Now, once again, very vague, but we think of gravitational radiation going outwards and inwards as traveling along light directions. So notice here, all future outgoing null radiation is eventually going to fall within my null cone. So if I think that I can, if you just believe that I can use cross-sections of my null hypersurface to measure the total mass that's contained within, as long as I slide my cross-section far enough to the past, I will eventually encapsulate all outgoing gravitational radiation. However, any ingoing gravitational radiation from infinity that I missed, no cross-section will ever capture, namely these. So what I see, in fact, at past null infinity along my Bondi mass is that it increases as I go to the future, because what that corresponds to here is me lifting this null hypersurface, and as I lift it, it is encapsulating that ingoing gravitational radiation. So we see that we have an increasing Bondi mass at scri minus. It will approach the total mass. So the more ambitious question is, if I take the area over 16 pi of my my black hole, is this smaller than or equal to the Troutman Bondi mass of this null hypersurface? So just like we could for that asymptotically flat Riemannian slice, we can calculate something called the Troutman Bondi mass of this null cone. And the question is, can I bound the square root of area over 16 pi of the black hole by the mass at null infinity? And why this is more ambitious is because this is increasing, I'm actually refining here the Penrose conjecture in the process. So that is roughly the null Penrose conjecture. If I take a null hypersurface that goes to null infinity, can I prove that inequality? Okay, so that's the introduction. So what's our goal for the next 2 classes? So our goal. So I would like to prove the null Penrose conjecture in my last lesson for an omega that's shear free in vacuum. Okay, a result due to Johannes Sauter. So that's our goal. And so what I'm planning to talk about for the rest of today, so I'll introduce the null geometry we'll need. And then I can specialize to null cones. All right, and we'll talk about what it means to have intrinsic and extrinsic geometry of a null hypersurface. And that will lead us to the structure equations. And then the fun starts, because then I'm going to go, as you can imagine, to our 2 most favorite examples, Minkowski and Schwarzschild. So it'll be very helpful for us to study examples of null cones in Minkowski, and we'll be able to characterize all of them. And that will motivate the total mass of a null hypersurface for us. So then I'll go on to talking about the example of Minkowski. null cones. And then in my second talk, we can use this analysis to talk about total mass and energy. And I'll do that by using, rather than giving you the tedious definition of what a asymptotically flat null hypersurface is, I'll just lean on our intuition for Schwarzschild. To do all the heavy lifting, and that will finally lead us to the Troutman-Bondi mass and the proof that I'm seeking to show. And then finally, provided I don't waste too much time, we reach our goal. All right, so that's what I'd like to do. Okay, so now no more hand waving. Let's look at some math. Okay. Yeah. Okay. Tell me if I need to move myself out the way. So, what is a null hypersurface? All right. Definition. All right, so a null hypersurface, I'm assuming, of course, we're always in four-dimensional space-time. So a null hypersurface is going to be a hypersurface, and when I take the induced metric, it's actually going to be degenerate. Okay, so by definition, a null hypersurface is a hypersurface such that the induced metric is degenerate. All right, so what are some consequences for this degeneracy? All right, so what does it mean to have a degenerate metric? It means I can find a tangent vector field everywhere on my on my surface. Okay, so consequences that has a trivial inner product with all other tangent vectors. Okay, so there exists a vector field in my tangent space such that, and I'll use my square brackets just like Mutter did, and this has to always be 0. Okay, so for all other tangent vectors, including L bar itself, right? Okay, so that's what it means to have a degenerate metric. But given that it came from a non-degenerate metric in the ambient space, there are some very interesting observations. Since G is non-degenerate, the first thing simple linear algebra tells us is that it forces the dimension of our space to be distributed to the tangent space of omega, but also to its normal bundle. All right, so because G is non-degenerate, it's a simple linear algebra consequence that you have this equality of dimensions. Now we know this is 4, right? And by virtue of this being a hypersurface, this is 3. So I must have a normal bundle of dimension exactly equal to 1, and that's of course therefore going to be spanned by this vector field L bar. And it's null. All right, so why is that interesting? Well, firstly, we have a tangent and normal vector simultaneously, which is pretty wacky. This is exactly TP omega. So that was the first observation. Secondly, because this metric G is non-degenerate, this actually uniquely identifies the tangent space, bless you, as all vector fields hitting L bar giving me 0. So this actually identifies the tangent bundle as well. Okay? Now, omega is a hypersurface. So I can express it as the level set of a function, right? So it's going to be some level set of some function v. All right, so even just locally, some v, and I'll call smooth functions in my manifold by this f. All right, so since it's a hypersurface, it's a level set of some function, and that means if I look at the gradient of this function, it has to be normal to omega, right? Well, we know what the normal bundle is for omega. It's just the span of L bar. So what I've just shown you is that this grad V must be null. So if you take an inner product of grad V, it must be 0 on omega. And the reason why I've moved everything over to this level set function is it has a really nice identity that we can exploit. All right, so we see that is equal to that, which implies grad V is identically equal to 0 on omega. Okay, so I'll leave this as an exercise, but there's a nice identity. If you use the Levi-Civita connection, D, and you look at the inner product of grad V with grad V, this is exactly 1/2 the gradient of grad V squared. Right? Which means taking an inner product with any tangent vector will give me 0. But remember, if I have a vector field that's identically equal to 0 by all tangent vector inner products, this must be proportional to L bar. So grad V must be proportional to grad V, which is proportional to L bar. So in other words, what all of this junk shows us is if I take a derivative of L bar with itself, I get some multiple of L bar back. And therefore, generators of L bar must be geodesic or pre-geodesic. For some kappa. And why is that significant? Well, it means that my whole null hypersurface is just ruled by null geodesics. All right, so omega is simply ruled by null geodesics. All right. So another way you can construct a null hypersurface is just to take a cross section and shoot geodesics off of it. All right. So that's a null hypersurface, just a collection of null geodesics. So what is a null cone? Well, that's just me being a little bit more specific about the topology of omega and some properties that I would like to see at null infinity. Okay, so what's a null cone then? Okay, so firstly, any questions? Still good? All right. So since we want the initial cross-section with the event horizon to be an S2, I'm going to take omega to be a cylinder. All right, R plus because I'm starting from sigma 0. Okay, and here the R plus we think of as being generated by the L bar, which we now know gives us null geodesics. Okay, so where L bar generates the R plus. So the picture that we've got then, now that I've specified this topology, is an initial cross-section sigma 0. I choose my L bar pointing to the past, and then I shoot geodesics off of it. And what we then see from this is a foliation. So if I look at level sets then for the affine parameter along L bar, this will give rise to a foliation of omega. Let's call that sigma s. Okay, a bunch of two spheres. All right.
So your cone will be referring to null hypersurface in the horizon.
Sorry, say that again? Eventually, yeah, we want the initial cross-section from which you shoot your geodesics to be the black hole horizon.
But this is what you call a null cone.
Yeah. that's right. Well, I mean, a null cone is just, this is the first definition. I want a cylinder. And the reason I'm writing it as going to null infinity is the second condition will be that it expands. The area of a foliation will go to infinity.
When you talk about null cone, what do you refer to? You refer to exactly this? Or?
Well, so far it's a null hypersurface omega that's a cylinder where the R plus is generated by a null vector. And secondly, I'm going to make a condition on the area of the cross-section.
So does it include since one?
Oh, okay, since, well, this is really just...
That's just a motivation.
Yes, exactly, yes. Sorry, that's, yeah, I should have made clear that that was not really part of the definition. It's just a motivation for why I'm choosing this to be the definition of a null cone. Yeah, sorry about that, thanks.
For general null hypersurface, is the normal angle marketable?
Say again?
Is the normal line always
I think yes, because it's an S2 cross R. And you always, well, the assumption I'm making is that it's not going to do anything well, anything strange. Well, I guess you will assume S2 is orientable, and you will restrict yourself, I guess if I was more careful, to spacetimes that are time-oriented, which just means globally you can choose a time vector field that points. You can choose a global time vector field, and then with those two combined, I think you can probably deduce that it must be orientable. But yes.
So your null cone is really about this S2 part.
Yes, you shoot geodesics off of it. Well, right now I'm just saying a null hypersurface. I've justified that a null hypersurface is a collection of null geodesics, and a null cone is going to be so far a null hypersurface that's an S2 cross R, where the R is generated by a path-directed null vector field. So that's going to give you a surface.
But that is true for any null hypersurface. The cone part is about the S2.
Yes. This is it. This is what I'm saying in all kind of. Okay, but so far this picture isn't encapsulated by this assumption. There's one more thing I need to assume, right? So we want this thing to be conical. What do I mean by that? Expanding. Near square minus. So what I mean is just that the determinant of gamma, which I'll define in just a second, is positive for S much larger than 1, where I've chosen a geodesic foliation all right, so I've chosen L bar to be geodesic. All right, so that's where the d by ds comes from. And what is the gamma? Well, that's just the metric along the foliation, excuse me.
So this is a 5 problem.
Yes, exactly. That's exactly right. All right. So now we can start talking about the geometry of this thing. That's exactly right. Yep. All right, so geometry. Before I do that, let me just make one comment. So we have a gauge freedom here by my choice of L bar. So that's going to be useful for us to exploit later. So notice, if I choose any positive function, on my null hypersurface, then simply by multiplying my vector field by this function, I can generate a new foliation, right? Another foliation. And let's call that sigma indexed by some parameter t.
You mean you take this and look at an uniform curve?
Yeah, so what you find when you calculate this quantity is that this is just going to differ from the background geodesic. So let's assume L bar was generating geodesics. Then the difference between dL bar L bar being 0 to dL bar phi is this quantity here. You get a multiple of L bar phi. So you're just trading in geodesics for pre-geodesics, and what that causes is the initial surface to propagate at different speeds depending on the point along the surface. So if you like, in the background foliation, we had a nice level flow. And what we've done by scaling with this phi is we've extended unevenly from before, and this gives rise to a foliation that's a little off center. So we can choose different foliations by choosing different phi. Okay? All right, so that's all I wanted to say. So that's 1 and 2 is what I'll call a null cone, and the last comment was just the ability to foliate with different choices of L bar. Okay, so we're going to need to study the geometry of omega. Yeah, so forgive me, I'll be spending this lesson just building this thing, and then next lesson we get to play with it a little bit more. All right, so for any cross-section of my null cone, omega will now be a null cone from here forth. So then what I can do on this cross-section is choose a frame. All right, so let's choose a basis of vector fields. And what we can do, because our omega is constructed from null geodesics, is I can lead drag this frame to the rest of omega. So what do I mean by that? So we can lead drag this frame field to all of omega. And we do so by solving the ODE L bar xi is equal to 0 for the two choices of I. Okay, so, well, there's some things that we need to check, right? So I've solved this ODE. That doesn't guarantee that what I'm extending is actually tangent to omega. So we need to show that is in fact the case, and that's just a simple calculation. So let me do it. So consequences of this extension is the following. Well, if we just look at a derivative of the quantity L bar xi, taking a derivative with respect to my parameter s is equivalent to hitting the inner product with L bar. So this is just dL bar L bar xi, and then the L bar propagates to the xi. But I've solved so that xi and L bar can be permuted, can be flipped. And notice that this is exactly kappa L bar times the quantity that we've taken the derivative of. And the second quantity, after you flip these two, you can bring out the xi, and you're taking the derivative of L bar, but remember, L bar is identically 0. So what we observe is that this produces exactly a multiple of the function we're taking a derivative of. So if my xi's were originally tangent to a cross-section, this starts off 0, this equation forces it to remain 0 along all of omega. So at least I can claim that this frame remains tangent by having solved this ODE system to omega. But we can pull out a little bit more. All right, so we can see here that this tells me that along my leaf at S, this is exactly this. This is of course 0. So we conclude then from what I said a couple of boards ago that the xi's are therefore at least sections in the tangent bundle. Okay, so that's the first thing we observe. The second thing we observe is if I take a derivative when any one of my xi's act on an S, this is just L bar xi. Once again, I can flip these. L bar hits S to produce precisely 1. So this is xi of 1, and that's of course 0. So this is true for all S, and that's what we need to satisfy in order to claim that this is exactly therefore at S, just a bunch of sections on the tangent bundle sigma S. So along my foliation, by extending these xi's the way that I have, I've actually extended them to all of omega, and they remain tangent. They will also remain a frame, i.e. linearly independent, just by the uniqueness of ODEs, right? So this is indeed a frame on each section of my foliation. Where was I? All right, so I guess I'll squeeze it in here. So this is a frame extension, if you like, to sigma S for each x, at each S. All right, so I'm going to use this frame to make sense of my geometry. So, yeah, I think I'll abandon this board. All right, how are we doing for time?
What? Sorry.
Yeah, yeah.
What is it? You're proving EDS XI is equal to 0.
So XIS, if I can show this as 0. So I've justified that xi is in the tangent bundle. So S is a function on my...
SIS is XI applied to S.
Yes, that's right. It's hitting this as a function. Sorry, yeah, S is a function on omega. S is the affine parameter, or it's the...
The vector field.
Well, S is the function that tells me what leaf I'm on in my foliation.
Yeah, but
X is a vector field, correct. I've
you
showed
apply the vector field
to the function. That's correct, yeah, exactly. Yeah, please keep stopping me. I don't want to go so fast that nobody knows what I'm doing. So that's exactly what I'm aiming to do here, is to show that xi keeps me on my choice of S.
The sigma S is a level set.
That's exactly right. Yeah, so what I've done is I just look at the rate of change. Because you have L bar, this flips, you see that it's xi of a constant at 0. So that means xi of S remains 0, irrespective of the S that I'm on. So each of these xi's are tangent vectors to the leaves of my foliation. And they will be linearly independent just by uniqueness of ODE.
You have parentheses of S.
Yeah, that didn't make sense. Yeah, yeah. I mean plug, yeah.
Yeah, because you also have parentheses of S implies about.
Yes.
That means different.
Yes, you're absolutely right. You're absolutely right. Yeah. So I guess to be more accurate, these shouldn't be here. Yeah. No, thanks for that. So you apply it to S. All right. So intrinsic geometry of omega. All right, so because of this, any tangent vector then we will be able to write then as a linear combination of this extended frame plus some contribution from L bar. Okay, so any tangent vector can then be decomposed in terms of the xi's and L bar. And that means when I look at the induced metric, so let's assume that I've got another tangent vector y, I can express this as xi, big Xi plus alpha L bar, yj plus beta L bar. But remember, everything that's tangent will get killed by an L bar. So all that we see here is an xi yj, capital Xi, capital Xj. So what we see here is that the metric on our foliation dictates the metric on our null hypersurface. I can write this as gamma ij at P, where gamma at P is the metric of the foliation that goes through P, the leaf of the foliation that goes through P. Okay? Now you might be tempted into thinking here, okay, well great, maybe it doesn't depend on anything other than the leaves of your foliation, but what if you have a different foliation? Well, if you choose a different foliation, the way that you modify this frame is just by adding on a contribution in L bar. So in fact, this is the metric of any embedding that goes through that point. They're independent of the foliation. All right, so this is very much just the metric of a cross-section that goes through the point P, and it doesn't matter which cross-section. Okay, so let me just make a side comment. If we choose phi, so let me just choose the standard coordinates on the initial section, sigma 0. Oh, that's probably a bad choice, right? All right, then if I modify my L bar to phi L bar, one can easily check the way that this modifies the frame field is by contribution in L bar. So if I just go and plug in that instead of the xi's that we have up here, you see I haven't changed anything at all. This is still the exact same quantity numerically. So this means that the intrinsic geometry... let me hold off actually on this, on this comment. So, okay, so gamma ij P is also independent of the embedding through the point P. Does that make sense? Okay, great. Okay, so that's not all of the intrinsic geometry. Because L bar is tangent to omega, you get some more intrinsic geometry from its second fundamental form, confusingly. So this deals with the metric. Okay, but since L bar of P, although it's normal, is contained inside the tangent bundle, we also get intrinsic geometry from studying the second fundamental form of omega. So negative of my omega, this I guess will serve also as a definition. What I mean, what my convention is for omega, is the inner product then going back to my decomposition for x and going back to my decomposition for y. And similar argument, the L bar hits the L bar to produce a multiple of L bar, which goes away. The only contribution comes from here, and vice versa. The L bar will contribute nothing on the y decomposition. So this is exactly xi yj dxi dxj. So I'm going to rewrite this as a symmetric 2 tensor chi bar. And notice this chi bar is exactly the L bar component of the second fundamental form of sigma. Okay, so that's the other contribution to the intrinsic geometry. Okay, so where chi bar is negative, L bar, the inner product of the second fundamental form through S of P, and similar arguments as before shows you that this chi bar could not care less about the embedding you've chosen. It just needs to go through P. So this very much is a geometric property of omega. It doesn't differ by different choice of embeddings. Okay, so the intrinsic geometry for our omega comes from, let's say, intrinsic geometry at P comes from the intrinsic geometry plus the extrinsic geometry for sigma P, sigma S, excuse me. All right. So gamma, little gamma, and chi bar. That's the intrinsic geometry of omega. So now, finally, let's talk about the extrinsic geometry. 10:30 to 12. Okay. Any questions so far? Hope I'm not going too fast. All right. All right, so to talk about the extrinsic geometry, I need a notion of a transversal vector on omega. And I'm going to choose such a vector to be null. So how do I get hold of this vector? So the notation I'm using comes from a book by Barrett O'Neill, just because it's my favorite. But what I mean by this is just a section in the tangent bundle of our space-time that's restricted to omega. More specifically, what am I talking about here? Choose a vector field along omega that has no contribution in the xi directions, has no inner product with itself, i.e. it's null. And finally, you need to specify how it behaves relative to L bar, and I'm going to choose the convention that it's equal to 2. Okay, so what we've got here is a null hypersurface. It's got a tangent vector L bar, you've got your xi's, and what we have is a null vector field.
This is obvious convention.
Yeah, they're just this. Just this. This is what I mean. Yeah, this convention is not due to O'Neill. This is due to, goodness, Christodoulou, Kleinemann. Did they come up with it? All right, so there we go. We've got a full set of vectors then on our null hypersurface. So what is the extrinsic geometry? Well, we have something called the torsion. So the torsion is a connection 1 form along the leaves of your foliation. What do I mean? You look at the tangential derivatives of L bar in the L direction. This is a connection 1 form if you think about it. All right, so we're almost there. So there's 2 intrinsic pieces to the geometry of omega. There's 2 extrinsic pieces. The final one is just the equivalent of chi bar along the direction of L. And then we're done constructing at least the data on omega. And then we can start talking about how it propagates along a foliation. Okay, so the last piece of the puzzle that we'll need is chi ij, and this is just simply this guy here. So notice I've now also constructed the second fundamental form of my leaves. Let me get rid of the s, because it doesn't matter. This is 1/2 chi bar L chi L bar. So if I want to find the mean curvature vector of my codimension 2 surface sigma, that's just going to be the trace over sigma of these 2 contributions, and we see this is exactly trace chi bar L bar. And the reason I'm showing you this is it will be helpful to realize that the inner product of the mean curvature with itself can then be given as a product of the 2 traces, okay, just by the condition between L and L bar that I've given you and the fact that they're null. All right, so there you go. That's the extrinsic geometry of omega. You get this 1 form and you get this symmetric 2 tensor chi. Okay, so the Penrose conjecture is a statement about the area of a black hole. For us, that will be a cross-section of omega and something near null infinity. So I need to be able to analyze the propagation of geometry along my vector field L bar. Okay, and this is described by what we call the structure equations. Say again? Oh, for this? So you're going to get twice this hits itself, but then you've hit a half. That's right. So let's see. Let me just think this through. So we get four from a half hitting itself. Then you get that twice, which brings it to a half, and then you have L bar hitting itself, which gives it 1. Yeah, don't worry. It took me a while to get that wrapped around here. The halves and the 2s. Okay, so let me just put that into writing. So for folks who need it in the notes. So we will need later on to interpolate between sigma 0 and scri minus, whatever that means. That just means as s goes to infinity. So we will need to propagate the data that I've just given you. How do you spell propagate? There you go. The geometry on sigma s. Okay, so what are those equations? So I'm going to, as you can imagine, give you the equations. I will prove the easiest ones, and then I'll leave you with some homework. But it's just going to be a bunch of derivatives and algebra, so nothing to worry about. So the theorem is the following. So firstly, if I look at the rate of change of my metric, to be more specific, the components of my metric, we observe this is exactly twice chi bar. Secondly, if I look at the propagation of chi bar,
you can assume S is a pi parameter.
No. No, this is general S. K not necessarily equal to 0. Yeah. I'll assume the general form. It's not much harder than the affine, so why not just include it? So so far I haven't assumed any affine parameters. I will try and be.
I always chosen according to
the L bar. Yeah, so L depends on the foliation, correct. But yeah, I will try and stay as general as possible, so we don't have to. I won't be hiding anything. Okay, so I'm going to write out these equations, and there will be a couple of new things, and I'll just use it as an excuse to throw in definitions simultaneously. So there's this alpha bar, ij, and then for some reason I'm raising an index in my chi bar, so I'll explain that in just a sec. All right, so I'll tell you what this is, and I'll tell you what this means. And then here's the contribution you get from it not being affine. You get a kappa times chi bar. That wouldn't be there if it was affine. All right, so I'll prove these two, and the next two I won't prove. You'll see why in just a second. So this is going to be the Gauss curvature on the section plus the inner product between chi bar hat and chi hat. Of course, you don't know what that means. Plus a half. Then you have the Einstein curvature tensor coming in. And that is all multiplied by the metric. And then we get a contribution 1/2 trace chi bar chi hat ij. And then we get plus, you get the permutation of that. And finally, 4 more to go, minus g ij minus the symmetric derivative on zeta. So that's a round metric, symmetric projection onto, let's see, what do we call that? The symmetrization of the covariant derivative. Minus 2 zeta I zeta j. And then finally the contribution from the fact that it's not necessarily affine. Okay, so you can see why I'm not going to prove that. And I think you're probably thanking me. And then finally, I need to tell you what's happening to zeta. But I mean, all of this will just follow. I'm going to give you a hint, and it's going to be a sneaky way for me to introduce another definition as well for number 3 and also for number 4. But if you're interested, it's really just a bunch of derivatives collected together. Nothing to be scared about. All right, so trace chi bar, we get zeta I back, and then we get 1/2. Now d here is d tangent to the cross section. Okay, so if I'm maybe I should be more careful and call it that, and then plus the contribution from the fact that it's not affine.
Oh, sorry, what is that? That's xi trace chi.
So here I'm not putting in the parentheses because you didn't like those, so it's hitting trace chi bar as a vector field.
Oh, okay.
Yeah.
Xi hitting trace chi bar.
That's right. Do you want the parentheses? Yeah, so all I mean here is you can think of this as d.
It's just when you put s there.
No. No. Sorry, that wasn't supposed to be interpreted as me getting a jab in, no. No, I'm just messing around. Yeah, so what I mean here is trace chi bar is a function now, depending on the foliation, but I'm hitting it with the frame that I've lifted along omega.
But you're also hitting k with chi.
Correct, exactly, yeah. So these functions are being hit with these derivatives. Yeah, because this is a one form and I'm giving you the components, so this will depend on which vector field I've chosen. Okay, so there's a bunch of things here that I haven't defined. So let me quickly use this opportunity to do that. So from now on, when I look at gamma and I put indices upstairs, you may have guessed that's of course just going to be the inverse metric along the leaves. And I'm going to use this to raise indices. Okay, so that's where this came from. I just raised the index using the inverse metric. Secondly, what is that?
You write gamma super index ij and then gamma inverse.
Yeah, just as matrices. From now on, when I put the indices up here, it just means this. I guess maybe I should put a square bracket.
Okay.
Like that? Is that better? Sorry, no. So all I mean is component-wise, it's the components of the inverse metric. Okay, so what is alpha bar? Alpha bar is actually the Riemann curvature tensor when I plug in an xi, an L bar, an xj, and an L bar. And I'll give you the convention that I'm using for that in just a minute. And you've also seen a bunch of hats. So what do I mean by a hat? Well, if I take a symmetric 2 tensor, the hat is just the trace-free part. Take a trace over gamma, and then get rid of it from A. Okay, so a hat, everywhere you see a hat, I've just subtracted off the trace part. And then finally, the double dot that I introduced, just to be complete, is just simply the contraction over those 2 tensors. Okay, so, whoops, there's the equations. So I'm going to prove the first 2 just because they're going to be really, well, firstly, they're not very hard. And secondly, the second one is going to give us a fundamental fact about a null cone. So let me do that. Yep, I think we're here. It'll be really quick, don't worry. The derivative for the metric is pretty much trivial. All right, so proof. Number 1. If we take a derivative d by ds of gamma ij, all you've done is you've hit the metric with an L bar. So that means L bar xi xj plus xi dl bar xj. You'll also get a feel for how these calculations work. And this, of course, because I've solved so that I can flip both of these. Because it comes from the second fundamental form, you know that you'll be able to move them together, and this will produce 2 times dxi L bar dxj, and that is, of course, exactly what I claimed, just twice chi bar ij. The other reason why I want to prove these two is we're gonna lean on these calculations in Minkowski. So it'll be good for you to see where they come from. So secondly, let's just quickly see what happens when I take a derivative of chi bar ij. So this is a little bit more interesting. So this is dl bar dxi L bar xj, and this is what I'm going to use as my excuse to give you the convention for Riemann curvature, plus leave the xi L bar alone, and then introduce, well, it'll be L bar dxj, but I'm going to be lazy and just quickly throw in that switch. Okay, so this will also allow me to give you what the formula for this is for later use. Okay, so I'll break this up into just two simplifications. So let's call this A, and let's call this B. All right. What?
Just erase the formula you're about to prove.
Oh, yeah. You're not taking notes, Muta? You're not taking notes?
I'm taking mental.
How are we doing? I'm still doing all right. All right, structure equations. So A, let's do A quick. So, okay, so A comes from the Riemann curvature. So let's see here. That's going to be xi L bar xj. And the reason why is because I'm using the definition for Riemann curvature where you put the what do you call that? The brackets of xi L bar up front, and then you do d xi d L bar of L bar. All right, and you'll see then this goes away just by the solution of just how I chose my frame, and then this gives me exactly the d L bar dxi L bar xj that we had. But now you've also got to deal with the subtraction. Okay. So this is what we have. This is what I'm going to be replacing it by. And notice that this thing here can be simplified because right inside here we get a kappa L bar. So if this guy hits the kappa, leaves the L bar alone, I get 0. There's nothing. So the only thing that it contributes is a minus kappa, and then I hit the L bar. And here you can see the kappa chi bar coming out of the formula. Okay? So this is alpha bar, but I have to permute these two to introduce a minus. All right? So what we see then, just to be clear, d L bar dxi L bar xj is minus alpha bar ij, and I have to move that over kappa chi bar. Okay, great. So there's A. B is very, very easy to see. Whoops. Ooh, I might have moved that, sorry. All right, so B, I'm going to pretty much leave as an exercise so that you don't fall asleep. Okay, so all we need to do here is notice that this is exactly chi bar ik xk plus zeta I times L bar. Okay, so that's just something I'll leave. It's an easy check. So what that means is if I take an inner product of these two, all we end up with is precisely the contribution from here because L bar makes everything go away. And there you go. That's part 2. Okay, just by putting the appropriate signs. All right, so 3 and 4, I told you I wasn't going to do, but I'll give you a hint, and the hint is also going to serve as a definition for what I mean by the Gauss equation that I would like to use from now on. So the way you show this is you use the Gauss equation, more specifically use the double trace of the Gauss equation. really, you'll see why I say double trace. Because it gives us the Gauss curvature on sigma minus 1/4 the mean curvature in a product itself. Okay, so we're talking about scalar. So I must have taken a double divergence, a double trace, excuse me. And here comes in the chi hat bar chi hat, and this happens to be equal to 1/2 the scalar curvature of the manifold M G L bar L minus 1/4 the Riemann curvature tensor L bar L bar L bar L bar L. All right, so there you go. I'm going to use this now as my Gauss equation as well. And then number 4 comes from the Cardassian equation. So I'll also use that as an excuse to introduce the Cardassian equation. G is the Einstein curvature tensor. Thank you. Yes, I should define this. So Ricci minus 1/2 drg. And then finally, any other questions?
That's a space-time scalar curvature.
That's right, yeah, space-time. The yeah. 4, I'll leave as an exercise. Maybe a little less painful, but the hint here is the double trace of the Cardassian. Well, excuse me, the trace of the Cardassian, not the double trace. Cardassian equation. And here I'm just taking one trace. And what we end up with is the connection on sigma you take the divergence of chi bar hat, you subtract off chi bar hat when you put in zeta, you add on 1/2 trace chi bar zeta, so everything here should be a 1 form minus 1/2 d trace chi bar, and d here is tangent, of course, to sigma. And this equals the Einstein curvature tensor L bar, and then you leave open the input for a tangent vector on sigma, and you subtract off 1/2 the Riemann curvature. L bar, leave that open for a tangent vector L bar. So there's the Cardassian equation that I'll be using later on as well. Okay. All right, so there we go, we made it. So that's the structure equations. So I claimed that the first two, mainly the second one, is going to be really interesting for us when dealing with a null cone. And the reason why is it gives us the Raychaudhuri equation, which forces a sign on trace chi bar. All right, so the mean curvature along L bar we can show must be positive from our definition of a null cone. Okay, so the corollary. The rate of change of trace chi bar is equal to -1/2 trace chi bar squared minus the square of the trace-free part of chi bar minus g L bar plus kappa trace chi bar. And this is called the Raychaudhuri equation. Okay, so that's really why we came. All right, so I need to give you these as well, just for completeness. So after you've found the propagation of chi, you can take a trace to observe this. And this is also a very important quantity. It's related to the stability of black holes, but we won't say too much about that today. Okay, and then finally, another equation would be to study the propagation of the Gauss curvature, and this is just minus trace chi bar times k. And Then you get minus 1/2 the Laplace Beltrami operator on your leaf, plus the double divergence of chi bar hat. Okay, so I'll just prove the first one, because we've done all the hard work, and it's an important quantity. So these follow from our structure equations. All right, and I think that will lead us to the end of today. Okay, so proof, it's just a nice calculation on indices. So 1, d by ds, trace chi bar is d by ds, gamma ij chi bar ij, and we have quantities from the structure equations for both of these. What happens when I take a derivative of an inverse metric? We know I get minus kappa ik, the derivative of the metric kl, and then Lj, and we know what happens when I hit the chi bar with my derivative. I have my gamma ij and a bunch of formulas that we now know from the previous theorem. Minus alpha bar plus the square of chi bar and plus kappa chi bar. All right. So let me just break this up quickly. Really what I should be calling is this B. The last two are trivial, right? So you can see immediately here I'm taking a trace of chi bar to give me the kappa trace that I've got in my formula. And this I'm dealing with here, and you'll see why. Okay, so A gamma I k gamma kl dot gamma lj chi bar ij. Well, we know now what the derivative of the metric is. It's twice chi bar. So this is just twice the inner product of chi bar with itself. All right, but I've raised indices. And this we can decompose into trace and trace free. So this has a half trace gamma ij plus trace free ij. And the same is true for the guy on the right. And now look what happens. This guy hits this guy. It's going to give me a quarter trace chi bar squared. And then I'm taking the trace of the metric, which is 2. Okay? Then this is going to hit the trace-free part and give me nothing. And vice versa. These two will hit each other, give me nothing. So all I get is the trace chi bar part squared times the norm of the trace-free part squared. And that's A done. At least that woke you up. Okay, so that gives us A. Excuse me, so let's see, we had a quarter, then we traced the metric, so that gave us a half, and then we multiplied by 2, but I'm going to keep the 2 by itself. I'm not going to multiply it through. So that's 1/2 trace chi bar squared, and then we see plus the square of the trace-free part. Okay. B, you can see now why I only lined the alpha bar contribution, because the other two we've kind of dealt with in A. So that calculation is actually interesting. So what we do here is we notice that the inverse of the ambient metric can be written as a half L bar L plus L bar plus gamma ij xij tensor. Okay, so why do I give you the inverse metric of the ambient space? Well, it means that I can deal with this trace in gamma. I can actually substitute in the whole metric because the other contributions go to 0. So why is that the case? Well, gamma ij alpha ij is then the trace over the ambient metric, which is hitting it with this. And let me just remind you what alpha bar is. Okay, so we have alpha, L bar something, L bar something. But then I have to subtract off the contribution that come from these two. So I have to get rid of a half L bar, put in an L bar, put in an L. excuse me, put in an L bar, put in an L, and look, that's 0, because these two, and we're anti-symmetric in those entries. And then finally, I put in my L, and then I have to put in my L bar. And once again, these two are anti-symmetric. So this can really just be given by the full trace, and that, of course, is the Ricci tensor of L bar, L bar. But now notice, what is the difference between Ricci and Einstein? It's a metric component, and you're plugging in two null vectors. So this is exactly G L bar, L bar. Okay, because L bar is null. And there you go, that's the... okay, so I guess I should put everything together. So, just to be clear, careful. How are we doing? Okay, good, we've still got some time. Okay. So, putting everything together, we have, and the reason why I kept the 2, so we get 2, wait, no, the 2 came from something else. So, I've erased now what I should not have erased. Where were we? All right. Yeah, we had a minus, didn't we? So we had a minus 2 coming from the derivative of the metric. And here we had a trace chi bar squared plus the norm of chi hat squared. And we added onto that the trace of alpha bar. So it was actually the negative trace of alpha bar, which is exactly minus G L bar L bar. Then we added on the trace of chi bar squared. So that's adding on one of these. And we had a kappa. So we have 2, we subtract off 1, and we get our formula. Okay, great. So I won't go through the other 2, but they can be done easily now that you know the structure equations. So 2 and 3 I'll leave alone. Okay, so the reason I wanted to do the first one is because it has importance for omega. So let me quickly prove why. So given our definition of a null cone, it turns out trace chi bar has to be positive. And I think that will bring us to the end of today. Corollary, trace chi bar positive on omega. So why is that? Okay, so I don't think anybody, I was hoping somebody would have introduced the dominant energy condition by now, but so I'm going to assume something called the dominant energy condition, which says if you take the Einstein curvature tensor, you're plugging any 2 time-like vector fields, they are going to yield a non-negative number provided that the inner product between these 2 are negative. So why do they have to be negative? That simply states that they point into the same, at every point in space, they point into the same component of a null cone in the tangent bundle. So TS. Now why would I assume, therefore, that the Einstein curvature is non-negative? Well, remember, if G is the energy momentum tensor, so if you imagine that you are an observer traveling along T, then GTS represents the energy density of matter traveling along a velocity relative to you, namely S. The energy density of matter along S. And this should, of course, be non-negative. Okay, so there's a quick reason why we call that the dominant energy condition. So what that allows me to claim then by continuity is that G L bar is non-negative. Okay, so the way we show